Okay, guys, we are going to talk today about transmission lines. And specifically, we're talking about transmission lines that we can represent as two-wire, use a two-wire model for. What is that? What kind of transmission lines are those? That's a coax transmission lines, like the actual cable wire going to your home, or the coaxial cable you might use in the lab. Usually you put your input here, and say you put a ground signal here, and then your output is on the other side of the transmission line. And then we have the other types that are popularly used and can have this two-wire model, or the microstrip, the strip line, and the coplanar. And you guys can go on the internet and look at what these things look like, but basically they're all transmission lines that you can have on printed circuit boards. So they're particularly popular and useful. So all these things, the coax cable and these type microstrip, strip line, coplanar transmission lines, if you're getting into microelectronics or printed circuit boards or any kind of electronics, are very popular, and you'll see these over and over again. So the model, the proof, or what we're going to show about how these things work will apply to all of these, and that's in fact what we're doing. So these are all, let's see, so this is kind of check mark what this isn't. So these are all this two-wire model works for these guys that I just wrote down. What it won't work for are things like fiber optic cables, waveguides. For these guys, these are still, are transmitting electromagnetic waves, but we can't use the particular methodology that I'm going to show you, the methodology of the two-wire analysis, to analyze these guys. So you can't, so these guys can't use two-wire analysis, and we need to basically do a much more complicated analysis. Then we need to actually use Maxwell's equations to analyze these things. Okay, so let's now look at what the two-wire model looks like. So the actual two-wire model. And so you have a wire going, we just usually draw it on top. We draw a wire on bottom. So this is wire 1, wire 2. And the assumptions we're going to make in our analysis is that the thickness of these wires, or that the wires are extremely thin, so the thickness is very small compared to the separation between the wires. So if D is the separation between the wires, and the thickness of the wires is T, then our first assumption, so assumption 1 is that the thickness is much smaller than the separation between the wires. Assumption 2 is that if we call L the length of the wire, that the D, the separation between the wires, is much smaller than the length. So those are the two assumptions we're going to make. And so let's take a look at, let's say if you had these wires in space, they're running parallel to each other. The distance between them does not change. Okay, so we've called the distance between them D, and we're assuming that distance stays the same everywhere. So if we look at the position, let's call this axis that the wires are running along, let's call that Z, the Z direction. Okay, and then we basically say, if we look at the position Z0 along the wires, and we look at a small distance right around Z. If you just look at this small strip of the wire, we see that this little strip has a capacitance associated with it, and that's because any two conductors in space will have a capacitance between them. So just this incremental piece has a capacitance associated with it. Also, any sort of piece, any wire going in space, or any, as it's any wire will have its own also inductance. So actually, let me change this distance to squiggly L, so I can call this inductance L. So this is distance L. And so there's a inductance L associated with this piece, and there's a capacitance associated with this piece. So our third assumption, by the way, for now, we're going to add this later, is that resistance of the wire is negligible. We're not going to look at the resistance negligible. I don't know how to spell negligible. So we're not going to look at the actual resistance of the wire. So if we think about current and voltage along this wire, again, if we just look at this little piece and this little piece, if we just look at this Z0 area, we can think of or call it current going in this direction. We call that I sub Z. There could be a current going there, and it's a function of the reason I'm calling it I sub Z is because it could be a function of location along the Z axis. And there might be a current I sub Z going the other way as well. Okay, and if I look at, I can replicate all these things. A distance, a small increment of distance delta Z away from Z0. So this would be Z0 plus delta Z. And we can repeat exactly the same thing for that new location. This new location will have its own capacitance, the same as this capacitance and this capacitance are going to be the same value if this piece of the wire that we're looking at is the same width. And then same thing with the inductance, will be the same value as this guy. And there'll be, in general, another current flowing here. I mean, the current, there's going to be a current here, and there's going to be a current here, and that's going to be the current at Z0 plus delta Z. And this current is going to be the current at I at Z plus delta Z. All right, and then we're going to make a further assumption. So, or I think this is our last assumption. So these are assumptions. Assumption 4 that the separation delta Z between these two spots is going to be much shorter than lambda, which is the wavelength of the waveform. So what does the wavelength of the waveform mean? Well, let's say the waveform that you have is, I don't know what's a good number, 10 megahertz. So example, example of lambda. Let's say the frequency, nu, so let's call this the frequency of the signal that you're looking at is, in this example, nu is 10 megahertz. So that's 10 times 10 to the 6th hertz. The equation in free space is F is C is equal to the frequency times lambda. So basically, if you have this is C is the speed of light in your transmission line. And so lambda would be the speed of light in your transmission line divided by this 10 megahertz signal. Okay, that would be the distance. So at 10 megahertz, I'm not going to do the calculation, but I think you're talking about multiple centimeters would be the lambda wavelength. So we're just requiring that this distance be much shorter than the operating frequency that you're inputting. Okay. So let's see here. Okay, so at any point Z, we'll have a current I of Z and a voltage Z. And at Z plus delta Z away from that point, we'll have I at Z plus delta Z and a voltage Z plus delta Z. It's just of current and voltages at these points. So in a general case, we can extend this sort of description to the whole line. So we can say that each section of the line has an inductance and a capacitance. And again, we've ignored resistance for now. So because each section has its own inductance and its own capacitance, and all of these inductances and capacitances are the same along the line because the separation between the line stays constant and the thickness of the line stays constant, we can define something called basically inductance and capacitance per unit length. So we can define inductance and capacitance per unit length. So L, the units are going to be in units of Henry per meter, and capacitance is going to be units of farads per meter. So because these are the same along the entire line, I can just keep track of just these two numbers, and then for any section of the line, depending on the length of that section, I can get the inductance and capacitance by multiplying the inductance and capacitance per unit length times the length. Okay, so these are the assumptions that we're going to use for our analysis of this transmission line. And again, this transmission line, so our assumptions, to summarize them a different way, the specific assumptions I've made here, but the assumptions put in a different way. The reason I'm giving you the assumptions in a different way, because these are a simplified analysis, and then over time we're going to add the important points to this analysis. So the assumptions are, we're doing we're looking at a uniform line. This means D and T don't change. The distance between the lines and the thickness of the lines don't change. It's uniform along the line. And 2, it's lossless, meaning we've ignored resistance. Okay, so we're gonna make those assumptions. Okay, so now now that I have made this, that basically I'm gonna not look at resistance, and I'm gonna look at this as sections of this line. I can draw it as a circuit diagram, just with the capacitors, and inductors. So let's see, open up this thing here. Okay, so let's say this was I'm just gonna draw, this is the 2 wires. We're just gonna, it's gonna have some point Z, and then there's gonna be another point Z plus delta Z, and there's gonna be a point Z minus delta Z, and so on and forth. There'll be another point Z plus 2 delta Z, and so on. So I can go on basically indefinitely. And again, this is the Z direction. Okay, so basically if you're looking at this from a circuit standpoint, I'm just gonna draw the capacitance and the inductors and the currents and so on. So I'm gonna just redraw this 2 lines and sort of circuit notation. So each point is gonna have a capacitance associated with it and an inductance associated with it. And then there's gonna be basically another inductance and another capacitance. So this inductance and capacitance are associated with this Z. And then I'm going to have another capacitor whoops, another capacitor and inductor associated with Z plus delta Z, and another capacitor inductor associated with Z minus delta Z, and it keeps going indefinitely. So if I just, that's what my circuit looks like. So there'll be another capacitor here, inductor, and it just keeps going in both directions. So at any point, we're going to have a current I sub Z and a voltage V of Z. The current's going to be going through this inductor, and the voltage is going to be across this capacitor. And then when I get to this point here, the current's going to be I at Z plus delta Z is going through this inductor. And the voltage across this capacitor is going to be V at Z plus delta Z. And so on and so forth. Okay, so let's see, what else do I want to say? And the value of this capacitance here is going to be the capacitance per unit line times the length of the sections we're looking at. And that's going to be the same value here. So it's going to be also C delta Z, the value of this capacitance. And this L is going to be L delta Z. So the inductance per unit length times the length that we're looking at. Okay, so now we can start doing our analysis here and trying to figure out how we can solve for current and voltage in this case, where we have these sections of capacitance and inductance that are in series with each other. Okay, so we're gonna, as promised, I'm only gonna use only Kirchhoff's voltage law and Kirchhoff's current law to solve this. Okay, solve this issue. Okay, so just as a reminder about Kirchhoff's voltage law and Kirchhoff's current laws, so here's a little aside at Kirchhoff's voltage law. It says that if I have a bunch of voltage sources, this could be any number of them, whoops, hooked up, the sum, if I walk across, if I do a loop across this thing from this point back to itself, or from really any point back to itself, the sum of the change in voltage is going to be 0. So it says that if I add V1, so it's the voltage across here, V2 and V3 to get back to this point, the sum of that is going to be 0. So this is Kirchhoff's voltage law. And Kirchhoff's current law says that if you have a node, a circuit node, and you have different currents coming into that node, could be any number of currents, then the sum of the currents going into the node are going to be 0. Okay, so we're going to basically use these two laws to come up with an equation for this line. So the first thing we're going to do is use Kirchhoff's voltage laws and look at what happens around this loop to come up with an equation for the voltage. Okay, so that's so use KVL first, and then so if I look at first, if I look at this loop first, I'm going to have a V sub z, and I'm going to put these guys as a function of time as well, because strictly speaking, they could all be also time dependent. The currents, the voltages can be time dependent. Okay, so that voltage plus the voltage across the inductor caused by any change in current as a function of time. So remember that V across in an inductor for inductor, delta V across the inductor is L change in current with respect to T. Okay, so I'm going to put that in there. So L delta Z is the inductance of that little section, and we basically get the change in di dt. So we've got this guy is this guy is this guy, and now I'm just going to subtract. Basically, the last piece going across here is the voltage across this capacitor, and that's going to be plus V at Z plus delta Z, comma T is equal to 0. So I'm just going to move things around this equation. So I'm going to get the voltages in together and the currents together. So I'm going to end up at V. And just keep my notation looking the same. V of Z plus delta Z is function of time minus V at ZT over delta Z is equal to minus L di ZT as a function of time. Okay, so I'm rearranging this equation to look like this equation. Now, if I take the limit of this whole thing as delta Z goes to 0, as when this delta Z gets very, very small, this is going to look like a differential equation. This is going to look like a differential term, because I got the 2 points over the separation between the 2 points in the limit as this delta Z gets very small. So what we're going to end up with is dV in the limit as delta Z gets really small. This is going to look like dV of ZT over dZ. That's equal to minus L di ZT as a function of time. So this is going to be our equation 1. And that's just purely from Kirchhoff's voltage law across this loop. Okay, so we're going to do the same thing with Kirchhoff's current law and look at the current basically going into this node. Let's see. We want to look at the current going into this node. Okay. So for that, we basically have, or any one of those nodes, it really kind of doesn't matter. Okay, so for each one of those, I have the current I at Z plus the current going the other way plus delta Z plus C delta Z dv dt is equal to 0. So as an aside, for a capacitor, oops, I is equal to C dv dt. So this current is the capacitance for that section times dv dt. That equals to 0. And again, if I take the limit of this thing as delta z goes to 0, I'm going to end up with equation 2, which is di zt over dz is equal to minus c dv zt dt. Okay, so these are the two equations I have to work with. This equation 1 and equation 2. Okay, so let's see. We can start by taking if I take the derivative. So I got two equations, two unknowns. Okay, so I'm going to try to solve it by taking the z derivative of this. So basically taking the double derivative of this thing. So that's for step 1. So I'm going to take this guy. So equation 1, take derivative of equation. Let me just do this on a separate page. So take the dz of equation 1. So you end up equation 1 is dv zt over dz is minus L di of zt dt. Then if I take the derivative of this, I have to take the derivative of both sides. With respect to z. And that's going to look like minus L I of zt second derivative but it's going to be respect to both distance or space and time. So that's first step. And then the second step is I want to take the derivative with respect to time of equation number 2, that being this equation here. So let me just copy that. So I'm going to take the derivative with respect to time of this side, and same on this side. So I'm going to end up with the double derivative of I with respect to z and t, and then minus c, the double derivative of v of z of t with respect to just time. Okay, so now what do I have? I have a this term here, and I have this term here. So it means that I can substitute this guy in for this guy here and end up with voltage on both sides. And I can do the same thing with the current because I have, I can do the same thing with the sort of the current equations. But so you end up with two new equations. So substituting terms, I end up with one equation that's ZT is with respect to is LC squared of V of ZT with respect to time squared, and derivative of 2I of ZT is respect to space is LC di of ZT over dt squared. So I end up with these two equations. Okay, so again, these equations are describing, this equation and this equation are describing what happens in this section of the line in terms of current and voltage flow. If I have a certain, if I have a certain voltage here, what's going to be the voltage here? Like what's the relationship? And we just use Kirchhoff's voltage and current laws. Okay, so we got to this point fairly simply, just by taking, the second derivative and doing some substitutions. So we're left with trying to figure out, okay, if we have these two equations and two unknowns, what are the solutions for these? So it turns out that deriving the solutions for these isn't very easy, but people have come up with the solutions for these types of equations, okay? And so the type of solution for these equations are called, and so I'm just going to basically tell you what those are called wave solutions. So these are general form of solutions for these kind of equations. And the general solution, I'll just write it down for you guys before I give you an example. The general form is you end up with something that's a function of time minus square root of LCZ, or another possible solution could be function of time plus square root of LCZ. So these are the general solutions for these two equations, and they're called wave solutions. Okay, and we'll see why here.